We're working once again on homework 2.5, equations of motion, and we're at question 6 right now. Question 6. Now 6 has parts A, B, C, and D. We're going to do here, actually I'm only going to do parts A and C. First of all, part B is conceptual, so we can talk about that in class. But we would do part A, C, and D, but D is a little bit longer, and what I'm going to do is I'm going to save that for the next recording. So right here, we're just going to do part A, skip B, and part C. So right off the bat, let's write down our givens. So we are driving through a town at 16 meters per second. So our initial velocity equals 16 meters per second. When suddenly a car backs out of a driveway in front of you, you apply the brakes and begin decelerating at 3.2 meters per second. So, of course, our acceleration A, the D in decelerating means minus. So it's minus 3.2 meters per second And once again, we can kind of conclude that our final velocity, since we're trying to brake to a stop, is going to be VF is going to be 0 meters per second. So A asks us how much time does it take your to stop. Sorry, that's a typo in the homework. How much time does it take you to stop is what it should say. So we have our givens written down, and our delta t, our change in time, is what we're trying to find out. Well, we have initial velocity, we have final velocity, we have acceleration, and we need to find time. Which equation relates them all best? But our first one of our 5, which is our final, which tells us that our final velocity is equal to initial velocity. Oops, that's not supposed to be an equal sign. Our initial velocity plus A times our change in time. So solving for delta t, what we're going to do is we're going to subtract VI from both sides. So VF minus VI. And then we're going to divide by the A. I'll just do this all in one step here. Divide by our acceleration gives us time, or delta t. So delta t equals VF minus VI all over acceleration. So our final velocity is 0 meters per second, minus initial velocity of 16 meters per second, divided by A, which is negative 3.2 meters per second. And actually, before we go on, look right here. If we hadn't made that acceleration negative, that would have meant that 0 minus 16, that would have given our final answer as being negative, and you can't have negative time. So this right here shows that the acceleration must be negative, as was indicated by the term deceleration. So if we calculate all this out, 0 minus 16 divided by negative 3.2, that comes out to be 5 seconds. So delta t, change in time, equals 5 seconds. That's how long it takes for us to stop. So we're going to skip part B. Oops, we're going to do part C right now. And then we'll save part D for another recording, like I said, because it'll take a little bit more. Well, in part B, we were supposed to try to guess what the velocity should be at half the time of braking. So at t equals 2.5 seconds, what would our velocity be? So that's what we want to write down right now. We're told at half the time, what would our speed be? So delta t equals 2.5 seconds. Well, our initial velocity is still 16 meters per second. Our final velocity is still, I'm sorry, we don't know what that is. Put a question mark there. And our acceleration, that's what I meant, is still the same. That's negative 3.2 meters per second squared. So, well, we can use the same equation as above. We're just solving for something else now. We're solving for our VF, our final velocity. So we don't need to rearrange this at all. We can simply write the equation number 1 as is. That's VF equals VI, initial velocity, plus acceleration times time. So our final velocity at half the time will be 16 meters per second plus negative 3.2 meters per second squared times, now it's 2.5 seconds. That's our time. So final velocity equals 8 meters per second. And regardless of what we guessed in part B, that is 1/2 of what it originally was. So time-wise, velocity and time are related on a linear basis. Half the time means half the velocity.